topic is analysis of Newtonian fluid behavior between rotating coaxial cylinders, which comes under transport phenomena. In this presentation, I will explain the theory, derivation, and numerical problems related to this system. In this system, we have two coaxial cylinders, meaning both cylinders share the same axis. The fluid is present in the space between them is called annular region. The outer cylinder rotates with angular velocity omega. The inner cylinder is stationary. The flow is steady, laminar, and purely tangential. Also, we neglect n effects. Means we only consider flow in the radial direction. Here, the fluid assumed to be a Newtonian fluid, which means shear stress is proportional to velocity gradient, viscosity is constant, density is constant. Here we consider the cylindrical coordinate system. These are the general momentum equations in cylindrical coordinates. We have r direction equation, theta direction equation, and z direction equations. This equation describe how flow moves under the forces like pressure, viscosity, and gravity. But in this problem, we will simplify them based on physical conditions. Based on the physical conditions of the problem, we can identify the non-vanishing velocity components and simplify the Navier-Stokes equations accordingly. Based on these systems, here Vr equals to 0. The radial velocity is 0. Also, the Vz equals to 0. And V theta is the function of r. Only tangential velocity exists. So, velocity depends only on radius. Also, in pressure distribution, pressure varies with radius and height. After simplifying the equations, we obtain the following reduced form for each component. For r component, we get minus density into v theta square by r equals to minus dp by dr. For theta component, we get 0 equals to d by dr of 1 by r into d by dr of r into v theta. For z component, we get theta equals to minus dp by dz minus rho into gravity. When we apply the boundary conditions, the velocity profile is determined by solving the theta component equation subject to approximate boundary condition at the inner and outer cylinder surface. In first boundary condition, at the inner cylinder surface, r equals to kappa r, the fluid velocity is 0 due to the non-slip condition. Here v theta equals to 0. And in second boundary condition, uh, the outer cylindrical surface r equals to capital R, the fluid velocity matches the rotational velocity of the outer cylinder, v theta equals to omega r. Now by applying the boundary conditions in the equation, first we integrate the equation, then we get this form of velocity. And now by applying the boundary conditions for the first boundary condition and second boundary condition, we get the velocity profile as omega into 1 minus kappa square into r minus kappa square r square into omega into 1 minus kappa square into 1 upon r. The final equations we get omega r into r by kappa r minus kappa r by r upon 1 minus kappa minus kappa. The velocity profile is a combination of the linear term and a hyperbolic term. Characteristics of coated flow between rotating cylinders. The profile depends on the radial position, angular velocity of the outer cylinder, and the geometry of the system through the parameter couple. Also, this equation shows velocity increases with radius, flow is non-linear, and it is the combination of linear plus inverse variation. Now the key results and observations. Here the velocity is 0 at inner cylinder and maximum at outer cylinder, and also the shear stress highest at inner cylinder. Also this system is used in viscometer to measure the viscosity. Now we move to the second numerical. Here the conditions given, uh, inner radius, outer radius, angular velocity, dynamic velocity, velocity distribution, and the A and B values. The velocity profile follows a non-linear relationship due to the 1 by r terms, resulting in tangential velocity varying across the radial distance between cylinders. In these questions, we are given these values. By putting these values in this equation, we get for A, we get V theta equals to 0.667 meter per second. For inner cylinder, R equals to 0.04 meter, we get V theta equals to 0 meter per second. For outer cylinder, we get 1.2 meter per second. Also, the velocity variation is velocity increases with radius. Profile is non-linear due to the 1 by r term in the velocity distribution equation. Now we move to the third questions. Here, rotating viscometer with two coaxial cylinders. We have to calculate torque, power, and work done for given operating conditions. Here the values are given. For calculating torque, we use the formula tau into 2 pi r square L. By putting the given values, we get torque equals to 0.178 Newton meter. And for power, we have formula tau into omega. By putting the values, we get power equals to 4.45 watt, and work done is pressure into time, which is 2670 joule. And also the viscosity effect is with a higher viscosity result in higher shear stress, which increase torque requirement and consequently leads to higher power consumption of the system. Now we move to the fourth questions. Here, fluid between two axis cylinders with outer cylinders rotating with the speed of 15 radian per second. Radial pressure gradient develops due to rotation. Here, the given data are density is 1000 kg per meter cube. Inner radius is 0.05 meter. Outer radius is zero point 0.1 meter. Angular velocity is 15 radian per second. Pressure at inner cylinder is P1 equals to 1 atm. We know the equations. Radial pressure gradient in rotating fluid dp by dr equals to rho, rho omega square r. After integrating this equation, we get this equation, and by substituting the given values, we get delta P equals to 843.75 Pascal. And also pressure at outer cylinder, we have P1 equals to 101.325 Pascal, and pressure at outer cylinder is P2 equals to P1 plus delta P. By adding this P1, we get 1 P2 is 102.168.75 Pascal. So the pressure increases outward. Now to conclude, We have the velocity profile is non-linear. Shear stress depend on viscosity, and the rotation creates pressure gradient, and this system is important in viscometer. Thank you.